Okay, good morning. Today we will continue the lecture, and now I will give the lecture about the influence of solid particle in the fluid flow. So before these materials, we have been discussing when the fluids only flowing through the pipelines or through some flow patterns. But today we will study how if there's another solid particles or there's addition of solid particles when included into the fluid flow. So why we put particles flow into the fluid mechanics lecture? Basically, because there's some application later when you deal with some operation in chemical plants, there will be some flow of the fluids that's also accompanied with particles. For example, do you know this? Can you guess the name of the device? What is this?
I don't know, sir.
Anyone can guess what is this one?
I'm not sure, sir.
This is a filter, or the complete name is plate and frame filter. So from the name, I think you can guess what is the function of the device, right? So to separate between, if you have slurry means you have a high amount of solid particles inside the liquid. So you need to separate, either you want to take the solid part or you want to purify the liquid part, and you need to use a filter. Just a sec. Okay, sorry, because some calls comes through. Okay, so the function of the filter is to separate between the solid and the liquid. Either you want to take the solid or either you want to take the solid. And this one is also a filter, but the name is the rotary vacuum filter. So it's like a cylinder, and you have this is the vacuum. So what do you want to separate? Is basically is the same, right? The solid you need to separate from the liquid, and then this is the place when you want to input the slurry one, and then this is the filter. And when the slurry, because there's a vacuum at the center of the cylinder, the solid will accumulate on the surface of the filter. And then you can take out the solid, or sometimes we call cake. Cake is the solid part that's separated from the filter. And this one is settling chamber, or sometimes it's called gravity chamber. By the name, I think you can understand that the function will be to separate the solid from the flow. Normally, is this for this one and this one, you separate the solid from the liquid. But this one, you separate the solid from the gas flow. So you are using the settling chamber to put the liquid into the down from this area by gravity. And this one is also separation of the solid from the gas, but using additional rotational movement of the device. We call it a cyclone or cyclone chamber. So if the gravity or settling chamber is only using the gravitational force, this one you are using the centrifugal force. Same like centrifugation, but for solid in the gas phase. Okay, and this one is a bit different from others. Yeah, this one is absorption column. So in an absorption column, do you know absorption? Or have you heard about the process called absorption?
Sir, is it absorption or adsorption, sir?
B1. There is two types of operation. We have absorption, and as a chemical engineering student, you need to know what is the difference. At least when you already graduate. Okay, absorption, the B1, is basically the process when you want to uh, clean up some gas. Means you need to reduce some component in the gas in order that the gas needs to be further processed. For example, LNG, not LNG, the natural gas. The natural gas, because before it can be processed into LNG, the liquefied natural gas, mostly the content of CO2, the carbon dioxide, needs to be reduced before it can be liquefied. Because if you liquefy natural gas with high content of CO2, the CO2 can solidify during the process, and it can damage the liquefying device. So you need to reduce the CO2. How to do it? You contact it with liquid. So the liquid will take the CO2 from the gas. But if you want to take the CO2 from the gas using the liquid and the gas needs to be in a good contact. So the contact between the gas and liquid must be in a good way. So you use the absorption column. So inside the column, you put what we call, where can I write? This one, packing. Packing is a solid material. So you put the packing inside the column, and then you contact the gas with the liquid. The function of the packing is to make sure the packing will have a lot of surface area, right? So in the packing surface area, the contact between gas and liquid will be happen. And this is also the example of particle and fluid flow, right? So actually, there are a lot of application between uh, a lot of application when we are dealing with solid particle in the fluid flow. What is the difference between absorption and adsorption? B and D. So for the adsorption using D, you want to keep some component either in the gas or in the liquid, but using solid materials. So solid materials will have pores on the surface, or sometimes also inside the solid. And the pores function is to take some component from the gas or from the liquid. It's also a solid fluid operation. It also has a column. So we also have adsorption column. The structure will be not different. A bit similar with absorption, but using different types of solid. Okay, this is some example of solid fluid operation. Do you have any question first from this one? Later, we will discuss some operation of this unit. Okay. Today I will give the explanation related to the concept first about the solid fluid flow. So basically, when there is solids in the fluid flow, there will be some differences between fluid and solid particle flow. It means when you have pipes, this. and you have fluid flow only without any particles inside the pipe, the fluid will be filling out the whole space in the pipe, right? Especially when the fluid is the gas. So the gas will be filling the space volume, and the flow, you can say that the flow will be continuous if there is no particles inside the pipe. So the flow will be continuous, the gas will be smoothly, the gas or the liquid will be smoothly flowing into the pipe. What happens if you have particles inside the pipe? Where the gas will flow if you have particles inside the pipe?
Around the solid, sir.
Yeah, around the solid, or you can say basically if you have particles inside the pipe, the gas can only flow between the particles, right? Or the empty space between the particles. We call it the void space. So there will be some, for example, you have the pipe length is L and the pipe diameter is D, then you will have V, right? You can calculate the volume of the pipe. If you have no particles, then the gas will be flowing through the all volume of the pipe. But if you have particles, then the gas is only flowing in the empty space or in the void space. And we will have what we call void fraction. Void fractions means void space divided by all the volume of the pipe. Volume of void space. This is the place when the gas will flow. And sometimes the gas will encounter some particles during the flow. It means the flow will be not continuous. It will some stop at a certain, and then they need to find another void volume, right? Like void space, so the gas can flow. So we can say that when we have solid particles, the flow will be discontinuous. It means it's not continuous. Maybe the term is not correct. It's not the smoothly continuous flow like without any particles. And also you need to consider the density of the particles is significantly higher, right, compared to liquid or gas. Even with gas, it will be significantly higher. And sometimes when the gas is flowing into the pipe and you have particles, some particles may flowing together with the fluid or with the gas. But since the density or the mass of the particles is significantly higher, then the particle can still can flow, but will be flowing with different velocity. So you can imagine, right, the story that I've been described to you, and also uh, the particle will flow with different velocity due to different density, and the movement of the solid particles will also be affected or significantly affected by the gravity because it has significant mass, right? It will have weight force. Weight force will be in that is influenced by the gravity. So during the particle flow, the gravity also have significant role in the solid flow. Okay, until this point, uh, I hope you can understand the basic concept when you have solid particles in the pipe together with the fluid flow. Okay, let me continue. Okay, some phenomena can happen when you have particles. First, uh, when you have solid and liquid or gas flow, you may encounter the collision between particles because maybe the size of the particles is different, so the weight is different, and then the velocity will be different from one particle to another. And then during the gas flow, the particles can move together with the gas but different velocity. And since the size is different, some particles can collide to each other. So there will be some collision between particles. And also there will be some collision between particles and the vessel or the pipe wall. There will be some collision and then some friction with pipe walls, with the particles. And also there will be some friction between the solid and the fluid. And then what will happen? If you have collision between particles and then collision and friction between particles and the vessel, and then the friction between fluid and solid particles. So the flow, basically, this is the cause why flow of fluid become discontinuous. Not what is the exact term in English to describe if the flow is not continuous or not smooth? Discontinued means stop, right?
Yes, sir. How do you say it?
So when I say discontinued, it doesn't mean that the gas flow will be stopped, but it's not as smoothly as without particles.
So it's something like inconsistent, sir.
Yeah, not
The
yeah,
flow
but
the
it's
flow pattern.
yeah, yeah, something like that. But I think you can understand, right? So the
Yes, sir.
the the effect of the solid particles to the gas flow or the liquid flow is making the flow will not be as continued as without particle. And some condition can also happen when you have solid in the pipe. First, you can encounter that fluid will flow, but the particle is in stationary. Okay. Or other phenomenon, you have gas flow, you have solid, and then the particles will move, but the fluid can still flow in the constant velocity. Stationary means constant velocity. Of course, this happen in just some part of the pipe. Okay, and based on the direction, sometimes the direction of the flow will be co-counter or sorry, what is the term? Counter flow and the same flow, the same direction. A particle and the fluid can move in the same direction or can move in opposite direction. Depends on the condition. Okay, this is the phenomena. Example of the phenomena or the flow characteristic. And then another characteristic is uh, the solid particle interaction. Another characteristic that you can find is regarding the velocity. So the particle maybe can flow with the constant velocity. Constant velocity means the velocity remains the same. And then the particles can travel in the together with the gas, but the different velocity, it means like, for example, is the accelerating one. Accelerating means the velocity is increasing with time. Sometimes it's also can decreasing with time. Okay, the constant velocity, I mean, this is from the particle side. From the liquid or the gas side, the velocity of the gas or velocity of the liquid can be the same or can be different. Or sometimes even if in the cyclone, the device that I have been showed you earlier, in cyclone, the particle can rotate during the flow. Okay, I think you can imagine the phenomenon. Okay, in this one, because some interaction can happen relating to the velocity, we have a term that's called relative velocity, or sometimes it's called slip velocity. So the relative velocity is the difference between the particles velocity and the fluid velocity. Why the particle velocity is not the same as the fluid velocity? Yeah, I have mentioned to you earlier, right? Because of the size, because of the density, because of the weight, and because of the friction. You can imagine that the particles can collide, can have friction with the wall, can have friction with the fluid. So there will be some unbalanced pressure or force distribution, and then it will have different velocity with the fluid. So during the, I mean, for the solid and fluid flow, normally we use the term slip velocity or relative velocity. This is the difference between the fluid and solid velocity. Normally, which one is higher?
Fluid, sir.
Yeah, usually the fluid velocity is higher. You can calculate the relative velocity by using this formula. It's uh, easy, right? Okay, so the figure you can see from this one, if you have a sphere, the solid is in sphere size, sphere form, and you have liquid flowing around the solid, you can represent the fluid pattern is like this one. So this one is the smooth continuous one. This one, what we call non-continuous or inconsistent. So see, this is the normal or the general interaction between fluid and sphere solid. Okay, in this one, and in this, I think in this area, the velocity of the fluid is uniform. And then when the fluid hits the sphere, what will happen? The flow will be diverted into two area, right? The upper area and the lower area. Okay, so there will be some pressure distribution in the particle surface due to the pressure of the liquid or of the gas, the pressure of the fluid. There will be some pressure distribution on the particle surface. You can put for different area A, B, C, D. This is the special area. In point A or in area A, what will happen at A, the velocity of the liquid will be at A, it will be 0 relative to the particle. It means at point A, the velocity of the fluid and the velocity of the solid is the same. Or the relative velocity is 0. Okay, at this point, it's called a stationary point, or normally we call it the stagnation point. And the characteristic of the stagnation point is the pressure or the static pressure at this point will be the maximum compared to other point. Okay, this is one characteristic in the sphere solid. And in particle and fluid flow, you can calculate the Reynolds number as well. You still remember, right? The formula of Reynolds number is density times diameter times velocity divided by viscosity. But for particles Reynolds number, the calculation is a bit different in terms of what kind of value that you need to use. So for the Reynolds number of the particle is the multiplication between the density of the fluid. So rho is the density of the fluid. D is diameter of the particle. Yeah, rho is the density of the fluid. D is the diameter of the particle. And then the velocity will be the slip velocity. The slip velocity is the difference between the solid and the fluid velocity. So you are using slip velocity for Reynolds number of the particle and the diameter of the particle, not the pipe. And it will be divided by the fluid viscosity. So the rho and mu is the same. It will or not is the it's will same with the fluid Reynolds number, flow Reynolds number. It will be the density and the viscosity of the fluid. But d is diameter of the particle, and the velocity is the slip velocity.
Sir, I have a question, sir.
Yep.
For points A, B, C, and D, will the U minus UP be different, sir, causing the Reynolds number to be different as well?
Okay. It will be different. So the slip velocity in A, B, C, D will be different. But basically, when you do the calculation of the Reynolds number, you do not use that slip velocity. You just use the velocity of the fluid in the continuous area divided the velocity of the particle as one particle. So you do not need to calculate each of these slip velocity. It's just the local slip velocity.
Okay, thank you very much, sir.
Okay. Any other question? Okay, if not, then I will continue. Basically, at A, the position will be the stagnation point. The slip velocity will be 0. At B, C, and D, the slip velocity will be not 0. There will be some effect of the friction in each point. And, oh, you don't have, okay. In this one, at the, I don't know if the flowing direction is this one. This is the front one or the back one. So I mean behind or in front of the particle. This one, there will be some phenomena that we call wind. Some turbulence that occur after the fluid, when fluid hit the particle, it will be divided, right? So the flow will be divided into upper and bottom, upper and lower area. And before the fluid is joining again in the continuous flow, there will be some wake, some turbulence that occur in the behind the particle. And the effect is there will be some additional pressure in this part. It's just the concept that you need to know. You do not need to calculate the pressure or something. And the so this one, right? So the in and the velocity in this area, the slip velocity in this area will be the highest amongst the all slip velocity. So we call it B, and C is the separation point. B is the upper separation point. C is the lower separation point. And then after the particles, there will be some wake, the recirculation or the turbulence created a flow pattern that calls wake. Okay. And then the pressure, this one, will be relatively low because there is what do you call it, more friction in this part. And actually the wake, this one, will be depending, the formation of the wake will be depending of the shape of the particles. For example, if you have very flat particles, actually it won't change the flow pattern of the fluid. Or if you have bigger particle, but you have, we call it streamlined body, there will be no wake occur here. Right? Okay, actually the higher the wake or the bigger the wake, it represents the higher resistance comes from the particles. Okay, any question? Okay.
All good so far, sir.
Okay. So we call it the resistance is as the drag force. So the pressure difference between the front part and the back part will create the drag force. And the drag force will be influenced by the shape. Of course, it will be influenced by the shape of the particle. We will have form drag is the drag force. Drag is means the resistance created by the solid particle to the flow, and friction will be friction between the the fluid and the surface of the solid particle. Okay, like this one. So this is the four types of shape of the particles. This is the completely flat. I think we don't have this one is completely flat particles. This one is the streamlined one. This one is the round shape or the spherical shape, and this one is called this one blunt body. And you can compare which one creates the higher drag and which one create the higher friction. For example, for the flat line, from the flat shape, there is no drag. There is a minimum or maybe 0% of drag created by the solid because it's not really give resistance to the fluid. So from drag or drag force is almost zero, but the friction, there will be a lot of friction created between the fluid and the surface of the particle. Okay. Then when what you call it, the cross area between the fluid and the particle, or the cross area of the particle that encountered by the liquid or the gas is higher, the drag will be higher. Because it will give higher resistance. So it depends on the cross area or the projection area. Projection area of the particle. So the higher the projection area, the drag will be higher. But if the travel of the fluid along with the particles is lower, then the friction will be lower. For example, in the blunt body may have higher or highest drag force, but it has very low or maybe zero friction. But again, the friction will also influence by how smooth the surface as well. It's like the normal friction concept that you have learned from previous lecture. Okay. Okay, now we go to the how to calculate the drag force. Basically, it's the same approach with when you want to calculate the friction force. You still remember, right? How to calculate friction force? You just finished the exam, right?
Yes, sir. Is it the 4FFL over D multiplied by U square over 2?
Yes, the FF this is the force in terms of energy over mass, right? Specific energy, friction specific energy. So you have this one, right? So basically, when you
Over 2, sir. U square over 2.
okay, I forgot already the
Okay.
formula. Okay, but you cannot forget. Okay, okay, this one basically you know F, right? F is the friction factor. How to calculate friction factor? It will be the function of
Reynolds number.
Reynolds number, and also sometimes it's also the function of
Epsilon.
this one.
Epsilon over D.
Yeah, the smoothness of the pipe. So the same concept apply to the drag force. Basically, to calculate the drag force, you need to calculate what we call drag coefficient. Drag coefficient is the drag force per area, the ratio between drag force per area divided by the density and the velocity. Or you can uh, use this equation. This is the drag coefficient. If for friction, we call it friction factor. In this one, we call it drag coefficient. So this is the force divided by area divided by this one. Or if you want to calculate drag force, you need to calculate the drag coefficient, then you multiply by this one. But what you need to pay attention, area is the projection area. We call it projection area. It means the area that perpendicular to the direction of the flow. So like if you have sphere and you have this kind of direction, the projection area will be, if you have sphere,
The vertical one, sir.
yeah, will be this one, right? So the area will become circle. The projection area of the sphere will be circle. And you can use the circle area formula to calculate the projection area. If you have cylinder, in a vertical form and the flow is like this, the projection area become
a rectangle, sir.
a rectangle. Correct. So the projection area will be the diameters times length of the cylinder. But if you have this one and the flow is this one, the projection area will be the circle, the area of the circle from the cylinder. So please be careful when you are using this formula. You need to make sure what is the projection area from the particle or from the solid. Any question?
Sir, for U0, it says
Mhm.
flow rate, right? Does it actually mean velocity, sir?
Yeah, this U is the velocity, and
Okay, sir.
mostly it's not the. This is only written flow rate, right? Usually we are using the slip velocity. Later we will check. Usually the velocity that you use to calculate the drag force is uh, slip velocity. And drag coefficient, similar with the friction factor, is a function of Reynolds number. So drag coefficient is a function of Reynolds number, but the Reynolds number of the particles, not the Reynolds number of the fluid. So you're using the Reynolds number of the particles formula. Okay, now there's some special case how to calculate drag force for very low Reynolds number. So basically, drag force will be depending first from Reynolds number, and then the second one will be depending on the geometry of the particle in terms of the projection area, and then it will create different why the geometry of the particles give influence on the drag force, because different geometry will give different drag form, right? Different drag forms, and then different friction form, different phenomena of the weight, and then uh, different drag coefficient on drag force. So there will be some different drag force coefficient for every geometry and every orientation. And how to correlate is by calculating the Reynolds number. You can have a curve diagram that correlate between drag coefficient and Reynolds number of the particles. But for certain case, for example, when you have small Reynolds number, okay, in this one, Reynolds number particles is less than 1. So basically, the drag coefficient will be inversely proportional to the Reynolds number. If this one is this one, right? This one for the fluid, but for the drag coefficient is 24 over Reynolds number of the particle. This is the special case number 1. For very small Reynolds number, usually below 1, then we can use this formula to calculate the drag coefficient. But for others, now you can use this type of diagram or graph. This is the drag coefficient. This is the particle Reynolds number. So for some geometry, you can see from this figure. Like for sphere, you can follow the sphere line. For the other types, for the cylinder, for the disc, then you can follow the straight line, different line. What can you see from this diagram? Compared to the FPS Reynolds number,
It's different, sir.
how different?
If the FRE, you can see like the lots of lines, right, sir? Depending on the epsilon as well, right?
Yeah, but the for one epsilon, for example, for the usually it's like this one, right? This one, and then this one, right? There is some bump in some certain case. But for this one, you can see depending on the geometry. For example, sphere. Sphere is this line, and then it will be decreasing, right? The drag coefficient will be decreasing when the Reynolds number is increasing until certain Reynolds number. This is the sphere one. Okay. At some point, the drag coefficient will increase again, a bit increase with the increasing of Reynolds number, and then will be decreased and then increase again. But for this one is this one. It's like just this one, right?
Why is that, sir?
Yeah, because that's the influence of the drag form and friction form. Like this is just this one, right? Flat one. Flat one, and then either at this position or this position, but there is no explanation, right? So it must be just one position. For example, you have this kind of this or this kind of this. There will be a constant influence of the drag form and friction form, right? So the the line will be just straight like this one. And at higher Reynolds number, the drag coefficient will be constant. But for the other one, for the sphere or maybe for the cylinder, you can have this kind of geometry. Right? So it gives additional or it gives different influence to the fluid depending on the Reynolds number. So the correlation is not just like this one. Sometimes at certain value of Reynolds number, it will be constant. Sometimes it decreasing, sometimes it's increasing. Okay. Yeah, you can find from the graph. There's a lot of graphs that you can use to get the value of drag coefficient. Okay, any question? Okay, there is some not conclusion, but some general rules or general phenomena that you can use, like for the sphere, like for sphere particles. Yeah, when the Reynolds number reach 3 times 10 to the power of 5, like 300,000, the drag coefficient will drop this one. So at this area, it should be around this area. And then this is because the boundary layer, like a lot of wake happens, a lot of turbulency happens, and then the separation point is move forward. That's why there is some uh, decreasing, very significant decreasing in the drag coefficient. So for Reynolds number between 1000 and 200,000, generally the drag coefficient is constant. For the sphere, the value is around 0.4. And then for the Reynolds number, the higher Reynolds number, above 500,000, the drag coefficient is also constant. So this is special case for the drag coefficient. Okay, now if you can try to calculate, or you can try to follow the calculation of the drag coefficient using this exercise. You have the solid particles with diameter of 2 millimeters, and then the average relative velocity of the air to the particle at the part that is not disturbed by the solid particles. So this is the slip velocity. The velocity is 40 meter per second. And then the density and the viscosity of the air is this one. So please calculate how much is the drag force. Okay. Please, there is some calculation at the next slide, but I will give you around 5 minutes to try to calculate and to check whether the answer in this solution is correct. Okay, I'll give you 5 minutes, and later we will discuss it. Okay, have you done trying? So first, please calculate the Reynolds number. So the Reynolds number of the particle uh, can be calculated by using this formula. Please check whether the result is correct. Make sure all the units is already the same.
It's correct, sir.
Yeah. So if the result is correct, then this one, when the Reynolds number is around 6,000, basically you can check using the one of the graph here. This is sphere, right? Spherical solid. So you can use either of the graph for the sphere. For example, this one. So for 6,000, what is the value of the drag coefficient? For this one, is it correct when the drag coefficient is 0.44?
I don't know how to calculate the CD, sir, because I don't know how to get the F.
Sorry, you can get the Reynolds number, right? And then just use one of the graph, for example, this one. Put 6,000. 6,000 is around this one, right? Between 1,000 and 10,000, right? So like in the middle. Just use this one in the sphere and take this one. Or you can use the more exact graph like this one. 6,000, where is it? It should be in this one. And then you can take this one. Yeah, around 0.4. Any confusion how to read the graph?
It's good, sir.
Should be clear, right? Okay.
Yes, sir.
So after you get the value of drag coefficient, then you put into the equation to calculate drag force. The projection area, since it is a sphere, so the projection area for sphere will be this one, right? The circle area. Okay, please check whether the value, the numbers is correct. Any question? Is the value of the drag force is correct? 1.56.
Sir, can I ask a question?
Yep, sure.
So to get the drag coefficient, you always have to look back to the graph.
Yes, normally yes, unless you are sure that the actually I have in the some slide. Unless you are sure that the Reynolds number is falls into special category. Actually, in this area, it falls into special category when the drag coefficient is constant. But for the sphere, the value is 0.4. Or if the Reynolds number falls to the very low Reynolds, less than 1, sometimes it's even less than 10. So for this one, this graph, this one, is until 10, right? So if the Reynolds number is less than 10, then you can calculate the drag coefficient using the formula. But actually, it's not really precise if it's already near 10. So maybe it's only precise until this one. That's why in the slide, if the Reynolds number is less than 1, then you can directly use this value. But if you have the graph, it's better to use the graph.
Thank you, sir.
But please choose the correct graph. Choose the correct graph and then choose the correct geometry.
Sir, there's a typo in the equation, sir.
Which one? Which one?
The diameter of no, not this one, sir. The just now the answer key, sir.
Okay.
For the last one, the last equation, how you find FD, the diameter should be 10 to the power of -3, sir, not to the power of -4.
Oh, this one.
Where it's 2 times 10 to the, yeah, that one, sir.
Okay.
Should be -3.
The diameter is this one.
2 millimeters, right, sir?
Yeah. Okay. 2
Yeah.
times 10 to the -3. But the result is correct, is it?
Yeah, the result is correct, sir.
Okay, it's just typo then. Okay. Any other question? Okay, can I continue?
Yes, sir.
Okay, now we will discuss about some phenomena uh, of the solid fluid movement. Previously, we discussed when we have particles or solid. Yeah, particles mean solid. We have solid inside the pipe and you have flowing fluid. Now we will discuss about the falling particle or falling solid. So you can put some figures like this. So this is the falling particles. This is the particle, and this is the fluid. So in falling solid or the falling particles, what is the velocity of the fluid? Velocity of the fluid will be, if you just have one particle, one solid falling down, what will be the velocity of the fluid?
The velocity of the fluid minus the velocity of the particles, sir.
The slip velocity will be the velocity of the fluid or this one or this one, right? You can calculate both ways. Just take the positive value. But in this case, what will be the UF, the velocity of the fluid only, not the slip velocity. This is the slip velocity, but this one, if you have falling particles, the UF will be 0, right? Because it's just solid going down. Only the solid that has velocity.
Okay, sir.
Understand, right?
Yes, sir.
Okay. So in this case, only for this case, not the previous case. The previous case is we considered both particles and fluid has certain value of the velocity. But for the falling solid, only the particles has velocity, and when we have the particles going down, the particles will have a change of velocity, or we call it du over dt. And we can derive the force balance. This is actually the force balance of the falling particles. This is the accumulation of the force, mass times du over dt. Du of the dt is the accumulation of the velocity, or what is the, this is called what? The change of velocity over time?
Acceleration, sir.
Acceleration, correct. This is the acceleration. Okay, so we can derive the force balance. it consists all the force that act upon the particles. What kind of force that experienced by the particles? First, we call it external force. External force is or comes from the weight force. If it's the gravitation, then the external force comes from the weight force, or we can put into the formula that the external force will be the mass of the particles times the acceleration. The accelerations actually can comes from the gravitation. It's just if it's just the falling particles, but if the particles experience centrifugal force, then the external force will be the centrifugal force. So for now, we just put it mass times acceleration. And then the direction will be, the direction of the external force will be downward, right? So we put it positive. And then there are two types of force that experienced by the particles, but upward in upward direction. First, remember the buoyant force. What is the formula of the buoyant force? Can you still remember? Density of the fluid
Rho GV,
gravitational or acceleration times the
volume of the particle.
volume of the particle. Correct. So you can put into this equation. Actually, this one is volume of the particle, right? Mass of the particle divided by the density of the particle will be the volume of the particle. So the buoyant force will be the density of the fluid. This one is density of fluid times volume of the particles times acceleration. If the acceleration is the gravitation, then you change A with G. And then the last one is the drag force. The direction is also upward because it's the resistance that experienced by the fluid. So the drag force, you can use the formula of the drag force. You calculate the drag coefficient first, and then, so this one, how about the UO? UO is the slip velocity. Because UO is the slip velocity and the velocity of the fluid is 0, then actually UO will be the velocity of the solid. So later we can correlate this one with this one. Okay, then just put all the component of the force into one equation. So the external force is plus, buoyant force is minus, drag coefficient is also minus because of the different direction. Then you put into the equation, then you can get this equation. So the accumulation of the velocity will be influenced by these parameters. Okay, any question until this part? Okay, if there is no question, then I'll continue. So basically you will, sorry, you will have this one, right? This is external acceleration or external acceleration. Then you can change if the motion or the external factor is the gravity, then you can change into the gravitational acceleration. But if the external force is from the centrifugal field, then you can change with this one. But R, pay attention, R is the radius of the particle pathway. So the radius of the pathway, not the radius of the particle. Yeah, so please don't be confused. R is the radius of the pathway. For example, if you see from the top, oops, then if the particle experience centrifugation or centrifugal field, then the movement is like this one, right? So R will be this one. R is not the radius of particle. Hati-hati ya. So this is the radius of the pathway. Okay, now you have this equation. This equation basically shows how much the velocity will change over time. Okay. When the particles falling, this is due to the gravity, right? So when the particles from the stationary state or from rest, I don't know if the term is correct. So from stationary phase in the rest position and then start to flowing, and you have stationary fluid. Stationary fluid means UF equals 0. Under the action of the gravity, we call it free falling condition. Basically, when the particles experience falling, there will be some acceleration period. There will be some acceleration period. It means U will be increased over time. So the velocity is not constant during the acceleration period, and it will be increasing over time. But actually, it's only happened in very, very short time. After that, the particle will experience constant velocity. This is what we call settling velocity or terminal velocity. So settling velocity or terminal velocity basically is the condition when the particles are falling with the constant velocity. Yeah, so for example, this is the ground and it's falling. So this is time boundaries, right? Like this one is acceleration, and then this one is falling or terminal, sorry, settling or terminal uh, area or the constant velocity. This is constant velocity. And you can calculate the velocity during the constant velocity, or you can calculate terminal velocity by using this equation, and takes this one equals 0. Okay, any question? So by taking account this one equals 0, basically what you need to calculate is this one, right? Or G is already constant, the density is constant, the projection area is constant, the mass is constant, then you just need to calculate the drag coefficient. So basically the terminal velocity will be function of this one. So in the gravity force, the velocity will be depending on the radius and other parameters as well. But actually the acceleration, what? Yeah, the acceleration period is very small compared to the constant velocity period, so it can be neglected, and then you can calculate the terminal velocity. This is the terminal velocity calculated by using the gravitational force, and the second one is the terminal velocity by using the centrifugal force. Please remember again, R is the pathway radius. Same, settling velocity or terminal velocity. Okay, what can you see from this equation? The velocity will be depending on this one, right? Betul nggak?
Yes, sir.
And then how to calculate CD? CD will be depending on velocity, right? Because CD will be depending on Reynolds number of the particle, and Reynolds number of the particle will be depending on the velocity. So actually, you cannot solve this equation straightforwardly. You need to do iteration, or you need to do trial error. So you are guessing the terminal velocity first, yeah, trial, not trial error, is it? Iteration. You guess the terminal velocity first, and then after that you calculate the Reynolds number of the particles, then you calculate CD, right? The other value is constant, right? Then you calculate the terminal velocity. You check whether it's already the same. If not, then you do the iteration again using the new value of terminal velocity. Can we understand, right? Unless the drag coefficients falls into the special case of Reynolds number. For example, later. Now, before goes into the explanation of this equation, just remind again when for the spherical particles, the falling velocity, you can use this equation. Of course, the uh, the calculation of the projection area is simple, right? Then you can calculate the uh, projection area using the circle area. Then first we will discuss the single particle. Single particles is only one particles falling down. Later we will discuss about the concentrated particles. A lot of particles falling down, or we call it hindered settling. But now we will discuss first about the uh, uh, single particles. Previously we have this equation, right? Let me clear this up. Okay, we have AP and we have M. M is the mass of the particle. AP is the area. Okay, the mass is the density of the particles times volume of the particles. Or you can derive into this one. And AP is the circle area. Okay, from this formula, is there any confusion? Should be okay, right? So
It's okay, sir.
you can use this equation. You can change previous one, this one, by change M and AP into this one. So the terminal velocity will be the function of the diameter of the particles, the density of the fluid and the particles, and then the G. But of course, it's still the function of the drag coefficient. How to solve this one? Still the same. You need to do the trial error, the iteration. First, you guess the terminal velocity, calculating the Reynolds number, then get the drag coefficient value, and then from the drag coefficient value, you put into this equation, you get the new value of terminal velocity. This is the normal calculation. You do the iteration or trial error. But for special case, first, when the Reynolds number is very low, when the Reynolds number is very low, Reynolds number, drag coefficient is function of Reynolds number, 24 divided by Reynolds number, and then the drag force you can directly calculate, and then basically the terminal velocity for single particles with the sphere shape at Reynolds number, low Reynolds number, then you can use this one. So it's not depending on the drag coefficient anymore. You can directly, when the falling particles, the spherical particles is falling, single, just one particles, then you can use this equation, the final equation, to get the value of the terminal velocity. But you need to know the value of the viscosity of the fluid. Okay, for the gravitational, this is for the gravitational field. For the centrifugal field, just change G become this one, omega r squared. Okay, and then for certain area, for example, 500 until 200,000 for spherical, we already know the value of the CD is constant at around 0.44. Then this one, you can change, you can just put into the equation. Then you can use this formula for calculating the terminal velocity. So basically, this condition apply for large particle fall into the fluid or gas with low viscosity, so it can have very high velocity. That's why the Reynolds number can fall into this range from 500 until 200,000. Okay, yeah. Any question? And this one is basically following the Newtonian law, or we call it Newton's law. For this one, we call it Stokes law. Okay. When you are using the centrifugal force or the settling or the terminal velocity is caused by the centrifugal force, actually you can change the G into this one, and the terminal velocity will be this one. You just change the G basically. Okay, for the very small diameters or very small Reynolds number, again it falls into the Stokes law. Then you can use this equation. This is the Stokes law. Reynolds number like around 0.2. Sometimes it's around 0.2, sometimes it's around 1. Basically, it's yeah, different textbooks sometimes give different value. It's like Reynolds number for fluid, right? The laminar, we can call it laminar region. The laminar region for the Reynolds number of the particles. Sometimes some books wrote below 1, sometimes 0.2, sometimes 0.4. Yeah, we just use this one, the higher limit. Okay, any question until this point? You do not need to memorize the formula. This is comes from the basic equation, this one. Then you just apply special case, this one for the spherical, and then for the very low Reynolds number, and then for the centrifugal, and then you change this one. So become this one. Should be the same, right? Same.
Sir,
Yes.
if in the exam, will like the graph be given to find the value of like CD?
I think so. Either
Or
the
should we like always have to do iterations, sir? Because
oh,
so
because
lazy, sir, to do iteration.
no. The exam no, but depends on the case uh, when the Reynolds number because the special case is only when the Reynolds number is very low or the Reynolds number are at the point where the drag coefficient is constant. So if the
Yeah.
Reynolds number is very low or uh, the drag coefficient is constant, then you do not need to do the iteration. Even if you have the graph, it doesn't mean that you don't have to do the iteration because CD is influenced by Reynolds number and Reynolds number is influenced by this one, right? So like this one. You can do without iteration only when the Reynolds number is very low or Reynolds number are in this region. If the particle is the sphere, if particles in the different geometry, then you need to check which one is the graph. Yeah, for this one. For the circular disc, then the region will be this one. It's longer. If you have a sphere, where is 500? So it's this one, right? From this one into this one. Sorry. Yeah, for 500 until 200,000, then you can consider the graph is in the vertical, sorry, in the horizontal line. Other than that, then you need to do the iteration. Okay, this one. Or you can use this one. This is for the sphere. There's other, there are others. Instead of graph, you can calculate the CD. For the less than 0.2, you use this one. Less than above 500, less than 200,000, this one only for sphere. And for the above 200,000 is this one. But If it falls between this one, you need to calculate. You need to calculate, it means you need to do the iteration. Okay? Any question?
All good, sir.
Okay, this is the example. That determine the terminal velocity of the dust particle with diameter of 60 micrometer. So this is the sphere. Micrometer is how much?
-6, sir.
Meters. And then the density of the particles is this one. Okay, air have temperature and pressure. Sorry, this one decimal. Kilopascal. Then from this one you can calculate density of air. Okay, please try to do this exercise at home. Check the Reynolds number. Not check the Reynolds number. For this one, you need to do the iteration. First, you need to guess the guess the velocity first, and then calculate the Reynolds number. Or you can start actually. Do you have a suggestion? How can you simplify the calculation?
I'm confused myself, sir.
Before doing the iteration, basically, you can see for this one, right? You can check this one first, like you guess the CD first. CD, then you put CD, this one, okay, this one gravity, right? So you use this equation. You use this equation. First, you guess 0.44, this one. You have all the value, right? G is okay, density of the particle is given, density of the fluid, you can calculate using the ideal guess. The diameter is okay, the diameter of the particle is known. Then you can guess first the drag coefficient is 0.44, then you can calculate UT. Then this one, after this one, you can calculate this one. Please find out the viscosity of the air at pressure at the temperature given in the exercise. Then if it falls between 500 and 200,000, then it's okay. If it's not, then you need to do iteration. Paham ya? Can be understand?
Yes, sir.
That's how you can start your iteration. Or you can start from this one. But still you need to guess, right? You need to guess the Reynolds number first. Okay?
Sir,
Yep.
for the equation to find CD using iteration, is that RE to the power of 0.687, sir?
Yep. But it's only for
Okay.
sphere. I think it's only for sphere.
Okay, okay. Thank you,
But
sir.
you can use the graph, right? Instead of using the calculation.
Yes, that's also possible. Is it allowed, sir?
Using this equation.
No, sir, the graph. Can we just look at the graph?
Yeah. You can use directly from the graph. That's
Okay,
the
sir.
graph 4, right? But to solve this exercise, you can start from guessing whether the CD is in the constant area or the constant range of Reynolds number. It means first guess the CD is 0.44, calculate the UT, and then calculate the Reynolds number. If above 500, below 200,000, then solve. The problem is solved. But if not, then you need to recalculate the iteration, doing the iteration to recalculate the value of the terminal velocity. Okay.
Okay, sir.
Okay, then we will discuss. One minor problem again. Tuesday, I cannot teach you at 1 p.m. because I have what? I have meeting in the afternoon. So last time when you have class with Pak Anggit, you shift it to Monday, right? Monday, what time?
Monday, if I'm not mistaken, from 1 until 3, somewhere at that time, sir.
Oh, but I cannot also at the time. Okay. Can you suggest me 1 hour replacement class for the Tuesday? Previously, I thought you are free after 3 p.m., but actually you are not free until 5 p.m., right? On Tuesday.
For Tuesday, we have classes from 3 till 5, sir. We have NMA class.
Okay. Okay, because my meeting is from 1 to 3. Okay, then I will give you option and then you can choose from the options.
Okay, sir. Sure.
Okay, thank you very much for today, and we will continue our lecture next week. Good morning.
Thank you.